Problem A4. The flow of heat through a material can be described via the thermal conductivity K. If the two faces of a slab of material with the thermal conductivity K, area A and thickness D are held at temperatures differing by delta T, the thermal power P transferred through the slab is this expression. A large flat lake in the upper Midwest has a uniform depth of 5 meters of water that is covered by a uniform layer of 1 centimeter of ice. Cold air has moved into the region so that the upper surface of the ice is now maintained at a constant temperature of negative 10 degrees Celsius by the cold air. An infinitely large constant temperature heat sink. The bottom of the lake remains at a fixed 4 degrees Celsius because of contact with the earth, an infinitely large constant temperature heat source. It is reasonable to assume that heat flow is only in the vertical direction and that there is no convective motion in the water. Question A. Determine the initial rate of change in ice thickness. Question B. Assuming the air stays at the same temperature for a long time, find the equilibrium thickness of the ice. Question C. Explain why convective motion can be ignored in the water. Some important quantities for this problem you can take from this table. Solution. Solution for question A. Determine the initial rate of change in ice thickness. So first, on a border of water and ice, we have temperature must be equal to 0 degrees Celsius. And now, because ice is very thin and water is very thick, so it means that we have rate of power going from this border to upper border of ice much greater than heat going from the ground to the border between ice and water. And this power difference will convert water to ice. And we can write the equations. So first we have power ice, which is going from this border between ice and water, and it's going up, and T0 that's 0 degrees, and T ice is negative 10, and this is total power. And the other power is going from bottom of water to the border between water and ice, and that's equal to this expression. Here we have T water equal positive 4 degrees, and T0 again 0 degrees Celsius. Now we can count what is the power difference, which will convert to latent heat fusion for water. That will be delta P equal P ice minus P water, and that must be equal to latent heat of fusion for water multiplied by speed of change of this mass of water to ice, and that's equal to LF multiplied by cross-sectional area multiplied by rate of change of ice growth multiplied by raw ice. After that we can find what is dH over dt. That will be this expression. Here we see that P ice much greater than P water, so we can neglect it. And finally we have this approximately this rate, which is about 2.6 centimeters per hour. This is the answer for question A. Question B. Assuming the air stays at the same temperature for a long time, find the equilibrium thickness of the ice. Solution for question B. Here we can use again the same expressions for power ice and power water, but now they are in equilibrium, so they must be equal to each other. But now we have to find what is thickness of ice and what is thickness of water. They are different. Because total mass must be conserved, we have this expression that d ice multiplied by rho ice plus d water multiplied by rho water equal initial d ice multiplied by rho ice plus initial d water multiplied by rho water. So we have two equations and we have two unknowns, and we can find what is thickness for ice and water. Now from these two equations, when we put numbers, we have these two equations. From the second equation we can find that d water approximately equal to 0.1 from d of ice. And when we put this to the first equation, we can find that thickness of ice equal approximately 4.9 meters. It means that thickness of water is about 49 centimeters. That was the answer for question B. Question C. Explain why convective motion can be ignored in the water. In the water, bottom part has temperature 4 degrees Celsius, and we know that water has maximum density for this temperature, and it's reducing when temperature going up to 0. So it means that in the lake we have water more dense when it's closer to bottom, and it means that there will be no convection. So that's the answer for question C.